Fantastic. So first and foremost, I'd like to thank the organizers for inviting me to share my work. I really appreciate this opportunity. So, I wear multiple hats. I am an assistant professor of medical oncology in the School of Medicine. And I'm also an assistant professor of computer science in the School of Engineering and Applied Sciences at Yale University. I was a past FDA guest researcher at the White Oaks campus, and then I also have an honorary professorship at the University of West Indies. So, as the title states, this is sustainable. The topic is sustainable software for practical biomedical applications. So for this presentation, the practical biomedical applications are those software tools that are being developed specifically for generating biomedical information and visualizations that will be used by the medical and biology communities for data interpretation and decision making that will add to the knowledge of the field as well as add to any decisions that are made about patients. As such, the risks naturally associated with these types of software should require a high threshold for quality and responsibility. So here I share an outline, and I will talk about three pieces of information. One, I will give definitions, and I say definitions plural, sustainable software. I will talk about challenges in the development, distribution, and maintenance of software visualization tools for academic research teams. I'll give a use case and then recommendations that we as a research team came up with as part of our learnings from the use case. And then I want to end out with talking a bit about software graveyards. And I'd want to preface this by saying that this presentation is literally my lens from a US perspective and of academic perspective, okay? So definitions of sustainable software. So there are two definitions that I'd like to share. One is the meaning for the software developers, and the other is the meaning for biologists and clinicians. So what is sustainable software for software developer, right? So these are tools and approaches that reduce digital carbon footprint throughout the software lifecycle by minimizing environmental impact, emphasizing energy efficiency, and emphasizing resource conservation. The users of the software visualization tools in an academic setting are either domain experts or novices. They will be biologists, clinicians, bioinformaticians, statisticians, or computational biologists. So the developers of these tools tend to be computer science researchers or software engineers. So because the users are generally not developers, they have a different needs and views on what is sustainable software. So for a clinician and biologist, sustainable software are tools and approaches that are reliable, accurate, safe, and stand the test of time, and therefore defined as sustainable, so capable of being maintained at length without interruption or weakening. So these are long-lasting tools. So we in the medical and biology field domains cannot use the mantra move fast and break things that the social media domain relies on. The software has to be usable from the very beginning and for many years to come in order to compare results or conclusions between biological studies or between patients. For that reason, we focus on aspects of software reliability from the vantage points of user needs and software development lifecycle. So reliable software is software that consistently performs its intended function without failure. It is resilient, maintainable, and dependable under a variety of conditions. So here I highlight requirements and challenges encountered while researching and engineering a software visualization tool to be used in the biology and medical space. Challenges and learnings will be highlighted using the key stages of software development lifecycle. So that's development, distribution, and maintenance. So we also share recommendations. And again, I just want to reiterate that this is from the perspective of an academic research team. So here's the project team for this particular case study that I'm going to share today. We have Dr. Mike Shaw, who's a senior lecturer of computer science at Yale University. He is a card-carrying software engineer who has been in industry for many, many years and has recently transitioned to back to academics. We also have my two students, one PhD, who's actually both now graduated, Sherry Hsu and Thomas Walter, who worked on various aspects of this project, and also Professor Holly Rushmere, who's the chair of our department and an expert in visualization tools. So it's no secret, software is a massive part of our lives. And the software we rely on continues to grow. So the software engineering behind any application is becoming more and more complex. The code base size of any given project usually grows. So let me set the stage. So what is the motivation? So we have three items that we need to address. One is the focus of our software tools, which is analysis and visualization. So specifically integrating multimodal and omics analysis with interactive output visualizations into clinical research and clinical practice. The second is the key requirement of our software tool, which is programming languages, which specifically require multiple programming languages for the integration, analysis, and visual outputs. And the third, but not least, is addressing safety from accidental breaches and security from intentional breaches. In the US, we have had severe security attacks in the healthcare space through ransomware and other malware. So what do we think, or what do we need to think about from a software engineering perspective for development, distribution, and maintenance? So for development, the focus is to build software that will be critical for domain experts and novices to process and visualize biological data. There are several considerations. One is the data sensitivity. So patient, clinical, or biological data will require high level of security and closed local environments, sometimes restricted. Collaborations are a requirement, a definite necessity, and critical for moving forward. And these collaborations need to be between domain experts and trained software engineers or advanced trainees such as graduate students to build the software. And the third requirement is actual prototypes, right? In our case, we required R and Python programming languages for data wrangling tasks that feed into visualizations made by D3's JavaScript, and also require operability on Mac and Windows operating systems. So what are our challenges? Obviously, communication between collaborators. So biologists and engineers have to speak to each other in terms that they both understand. We have to be able to use, integrate, and work across boundaries of multiple programming languages. And this is not trivial. You know, it's not common for software engineers to have expertise in multiple programming languages such that they can expose and resolve problems across programming languages boundaries. So what about distribution? So the focus is literally just packing up and securely delivering the software. And the considerations are installation on computers with purposefully limited network connectivity and strong firewalls for secure networks. Clients' machines may also have other specifically configured software that is brittle and cannot be allowed to conflict with other new installed software. And then the final consideration is that we need to take into account that installing and setting up software does actually take time. So what are the challenges? So differences in operating systems on users' machines results in differences in dependencies and their implementations. Extended length of time required to install and resolve the dependencies may vary greatly. And for our use case, it ranged anywhere between 25 minutes to 2 hours. So for maintenance, the focus is very simple. Just keep the software working over time, right? The considerations are that we have transient builders. So these are software built by users who may leave. So these are employees who leave or graduate students. We also have other considerations such as the expertise. The expertise is hard to replace in niche domains as the software is fairly unique. We also need to consider how long should the code or the project live, as this is a question that should be asked early, as it may influence how software packages and dependencies are chosen. It also highlights the need for standardization of workflows, processes, and provenance to facilitate seamless transfer of expertise and maintain the history of the software throughout the lifetime. So what are the challenges, right? And in maintaining this software in an academic research environment. The bottom line is that we do have a high turnover rate for developers in these niche areas. We have complex dependencies within packages used in the software tool. And honestly, the bottom line is maintaining software across different operating systems, different programming languages, and different versions of standard libraries is difficult. So here's our research case study. This is a software project of approximately 3,500 lines of primarily Python and R code. That's a small project. We require that it be deployed on both Mac and Windows machines. The project is literally about a visualization tool that is to be used by medical biologists and clinicians. As we were putting together this project and running through the process, we ran into two key problems. One, as I mentioned previously, we had up to 2 hours. It took up to 2 hours to install the environment and the dependencies. And then the second is that there was a unique installation error on every single computer system that we install the tool on. And so we had no idea of what could potentially be happening. So let's take a quick look at what visualizing the R code. And that's literally just the R code, not the Python or the JavaScript, just the R code, which is approximately 2,000 lines, looks like. So this is it. So each node represents a package in our project. Orange are the packages that we call. Blue are the dependencies of those packages. Each edge represents a link to a dependency. So in essence, we called 19 packages, which are labeled in orange, nodes, but over 100 packages labeled in blue were brought in addition to the 19 packages that we call. But where did all of these nodes come from? And why are they all tangled into a hairball? So the software visualization from the previous slide shows the greater problem. The code we write has many hidden dependencies from which we rely on. This is nothing new. This is what we know in the field, right? The problem becomes more challenging when we add different programming languages into the development. The complexity of the challenge increases even further as this software must run on multiple platforms. So different dependencies were observed for each operating system. And the package managers brought in different versions of the dependencies from different operating systems. So there was literally a lot of complexity that circled around this type of development. So why is this a big problem? So in some domains, the software engineering move fast and break things works great. So that mantra works great, right? However, this mantra does not work for safety critical or medical software. With so many hidden dependencies, how do we know how our software actually works? How do we know it will work tomorrow? How can we test so many moving pieces? So for the specific software that needs to last, so that is, those unique softwares from our clinical research labs or our medical biology, we need to think about the time frame the software needs to last, and how to manage the complexity. From a small project, literally just 3,500 lines of code, we get an explosion of software dependencies. So even the documentation in R admits the common way of bringing in packages may indeed cause confusion as to what is brought in. It's not all bad news, okay? So from our case study, we learned a few things that we can do better. So here we share recommendations based on our academic research team experience. So for development, use well-documented tools that meet your needs and choose a software methodology that matches the needs of your domain. And then second, and this is very important, take care to set up early continuous integration of multiple platforms if multiple operating system support is needed. When you do this on the back end, it tends to create a lot of troubles. When you do this on the front end, it tends to create a lot of problems on the back end. The second is the distribution. So installing virtual machine or Docker could be, and I stress could be, an option with some caveats, right? So virtualization may not be a viable option wherein security, privacy, and access restrictions are required. And this is especially the case when we're using clinical data. Virtualization may not be a viable option where resources are limited. So, for example, in low socioeconomic environments, in rural areas where there are limited or unstable internet bandwidth. And this is something that I think that we've all seen, is that performance may be lost through virtualization or performance-intensive visualizations in general. And all of the tools that we create in my research group are performance-intensive visualizations. So the second recommendation is archive successful binary builds. This is critical, but as we all know, this is not bulletproof, especially on Windows systems, as Microsoft does a lot of frequent updates, and those updates can cause challenges with even your archive binary builds. The other piece is to ensure packages, major, minor, and revision numbers match. SimVar is a wonderful convention that you can use to facilitate standardization. And we mention this because we found instances where package managers for different platforms matched the major and minor versions, but did not have the same revision number or bug fixes. And then finally, import dependencies and packages judiciously. If you only need one function, for example, it may be best to just implement that functionality yourself. So what about maintenance? So ask how long the visualization should live. This may inform where to spend time in software development and what dependencies may be critical, or otherwise how dependencies are selected for the duration of the project. And I will tell you that as you combine multiple programming languages, the development actually is quite long and a bit laborious. And so you want to make sure that you have clarity on this point up front. The second piece is to standardize workflows, process, and provenance to facilitate seamless transfer of expertise and maintain the history of the tool throughout its lifetime. Sometimes you have staff and students for a semester. And so that project needs to move forward after that staff or that student has moved on. And then third, generate dot graph visualizations that show the extent of the dependencies. We believe over time, this practice could lead to more hygienic, easier to maintain code with fewer dependencies. So here we took a deeper look. An example of generating and visualizing dependencies was performed for two of our guidelines. The first is import dependencies and packages judiciously, and the second is generate dot graph visualizations that show the extent of dependencies. We believe that this is something that can further be added into continuous integrations for testing and measuring dependencies. So static analysis tools should be leveraged here. Most programming languages have these already built in. So the examples on the right hand highlight in orange one package we called in, and shows in blue all the dependencies that were brought in with the called in package. And so this gives actually the developer a really good sense of where things can be better optimized and managed on that package level. So what happens when we do not address dependencies and other issues in software from academic research? We get software graveyards, right? And so these software challenges and other challenges, such as hardware or infrastructure, lead to software graveyards, which I define here as unvalidated and unmaintained software. So how do we tackle software graveyards? We need to get a deeper understanding of the key endpoints and reasons for graveyards in academic environments and identify opportunities to rescue software if desired. So let's talk about the reasons, right? Is it as simple as running out of money and or students? Or is it that the software tool is now obsolete? Or something else, or a combination of many things? So what are considerations that we need to think about when we tackle these software graveyards? We have 4 key major things that I thought are useful. One is the users, the builders, the stage of the software, and challenges, right? Our users, as I mentioned, are the biologists, clinicians, bioinformaticians, biostatisticians, and computation biologists. Our builders are the computer science researchers and software engineers. And in the academic setting, these are mostly going to be trainees. When we think about the quality of software and therefore reliability, I think about the stage that the software is in. And so for me, I bucket this into 3 groups. The first group is more theoretical, right? So this is the early point where you have some sort of idea that you will give a demo to show a proof of concept. And for the users on the call, who may not be used to this type of system, you need to be aware that a proof of concept does not necessarily mean that the product is actually a usable software product for your needs. The second stage is what I call more software that's ready for application. They're literally ready to go. They have been vetted by a peer-reviewed audience. They have proper controls and validation that they do work as they are intended. And then the last one is software as medical device. So this comes from my interaction and collaboration with the FDA. This is literally on the extreme end. And when I say extreme end, this is literally any software that is intended for clinical use, such as diagnosis, treatment planning, or monitoring, has to be approved in the US by the US FDA. And these particular software tools go through very rigorous assessment to make sure that they do what they say that they're going to do, that they are sustainable, that there is ample documentation that surrounds this throughout the entire life cycle of the tool itself. And as you can imagine, this is really a must, right? Because the risk is high. When these software tools that are created are wrong, you know that people can die. So this is a necessity, I think, for these types of tools. And then finally, we can talk about challenges, and those challenges that we discussed previously, right? And so these are the things that come into the software graveyard. So how do we transition from software graveyards into sustainable software? And so I came up with a few possibilities. These are not exhaustive, of course. So maybe we need to think about, collaborations, have mechanisms to facilitate and foster collaborations. We may also want to think about leveraging agentic tools, to assist, and I repeat, assist with distribution and maintenance. We may want to also rethink how we do the oversight of these tools. There are several wonderful package repositories that exist and some that have strict subject matter requirements and quality standards. So the examples here on the left are of 4 repositories, 2 that are strictly regulated in Black, so both of those are our packages repositories. The top one is CRAN, which has approximately 15,000 packages. The bottom one is Bioconductor, which has approximately 2,500 R packages. And then as you see, we also have ones that have no requirements, and so there's no quality standards, so to speak. The Python, the PyPy, has approximately 600,000 packages, and GitHub has approximately 420 million repositories, which with a significant amount being software packages, but it's unclear how many those are. And so there are systems set up there that can have varying levels of oversight. The second oversight that we may want to think about, depending on the use of the package, is some level of regulation. I gave the example of the software medical device that's for anything that's going into human beings. But we may also want to think about, some level of oversight or regulation for those software tools that will be helping to make decisions or draw conclusions or add knowledge to the biology or biomedical space, right? Because we make decisions that go into, the humans actually are taken from those software tools as well. So with that saying, the last thing that I would thought about in terms of oversight is actually putting disclaimers or statements in publications or websites acknowledging the status of the development pipeline, letting people know, especially these users who are not going to be, the computer science researchers or the software engineers, letting them know that, the tools which are literally still in, from the most part, the theoretical stage, versus those that are in, the more application-ready stage. So here I'd like to take a pause and have a discussion. And I can't, unfortunately, see you guys because it doesn't allow me to do this, but I have questions for the group. So this is an international group, and as I said, what I've just been discussing is literally from the lens of a U.S. perspective, right? And so I want to hear from a U.S. perspective and an academic perspective. And so what I'd like to hear from you guys is, literally, what is your experience with software graveyards? What do you feel are the cause or causes? And having any thoughts on solutions? And is this really a problem that should be solved, or should we let just the software die? And so I'd like to open this up at this point for a bit of discussion. And again, my apologies, I can't see you because of how the software is, how the Zoom is configured.
Yes.
Okay. So thank you for that robust discussion. So how broadly applicable are these recommendations for software development lifecycle and software graveyards, right? And so this is the conversation between industry versus academic software. So from our engineering experience in industry and experience in designing research for medical and biology software, we believe that in both industry and software born in academic environments, there's just many similar commonalities. So it's important for academicians and industry to communicate these challenges and find solutions, and hopefully find those solutions together. And the motivations may be different, but ultimately there is a common goal of building good and long-lasting software. So my closing thoughts are that, I presented a case study of known software dependency problems. And again, these are not new and novel. We know these, right? But we have not tackled these. So I've presented a case study of known software dependency problems that significantly impact software development, delivery, and maintenance when multiple programming languages are combined. So this is, I think, is going to be something that's going to be the wave of the future, is that we're combining multiple modalities to get the data from start to finish in our biomedical space. And so we need to really tackle that. So there's a lot of work that needs to be done to resolve these challenges. And then talking about software graveyards, so addressing those challenges that lead to software graveyards will help us to ensure that the software that is used in the medical and biology domains are reliable, accurate, safe, and long-lasting. And it may help to support the software developer's definition of sustainable software to reduce the carbon footprint throughout the software lifecycle. So anyone who's interested, so I think that these challenges need to be tackled by the community, and anyone who's interested in collaborating on this, please shoot me an email. All right? And that's literally all I have. So thank you very much for your time. Any questions?